Hello and welcome to this introductory video in which we're going to take a look at what is the force on a current carrying wire exerted by some magnetic field. So we're going to take a wire, we'll put it into a magnetic field and determine the force. So let's go ahead and set that up. We'll have a wire. Wire will be our nice typical cylindrical wire. Has some length L, some area A at the top, pi r squared if we care. Could be a weird shape, but let's just draw it this way. It's just got some area A and some length L. And let's now imagine that we put it in some magnetic field. Doesn't matter what the direction is, but we'll make it coming out of this board everywhere. Now let's ask the question, what is going on with the force? Okay. So we know how to think about this. Let's put in the direction of the current. So the direction of the current, let's say, is going up. That's my I. Well, what does that fundamentally mean? It means we've got lots of little charges in this wire, and they are moving upward if we're pretending that the positive charge is flowing. So lots of little pluses flowing with some velocity flowing across here. And therefore, we have moving charges in a magnetic field. They are moving perpendicular to the field, so we know that we are going to experience a force. So how are we going to calculate the force? Well, it should be the total charge times the velocity of that charge times the magnitude of B times the sine of the angle between V and B. In this diagram, I've set it up so that they're perpendicular because my velocity is up, the B field is out of the board. But I'm just trying to be fully general. Let's not worry about the fact that we know that in this particular case, as drawn, this part sine theta would just disappear because we're talking about 90 degrees, so we would get 1. But let's ignore that, keep it in there just for generality. All right, what is the total charge Q that is flowing through here? Well, let's imagine that in this wire, I've got some number density of protons. So I'll talk about N. This is the number of protons. And why are we talking about protons? Well, again, by convention, we're thinking about positive charges flowing. Even though we know it's not true, that's the way everything is defined. So we'll stick with number of protons per unit volume. Okay. So then what? These are pretend flowing protons. This is the number per volume. And of course, we can write that as the number per unit area times length, or volume is certainly area times length of that cylinder. So, okay, each individual one, there are n of them per unit volume. So we take n, we would multiply by the volume to get the total number that are flowing through here. They would all have a charge, that's QE. They're all moving with velocity v. And then there's a B sine theta. So this form of the expression doesn't seem all that useful, not all that intuitive perhaps, but let's just rearrange to make it something slightly more friendly. So we'll do N times QE times A times V. Then we'll put our L, B sine theta. All right, so why have we done this? So we expanded our Q to be all of that, right? And then we're now rearranging all of that business to sort of look slightly more useful. So by regrouping, what is this part? Well, N times QE is some total charge per unit volume that's flowing through this entire length of the wire. But what do I want? If I want to talk about this current, I actually want something, how much charge flows through a piece of area at some given time. So if this is the number per volume and I multiply by area, then that gives me just how much is in that little disk, basically. And if I multiply by the velocity of the charges, that then actually tells me how much is flowing through there. So I've got the charge per volume times the area gives me the charge that's going through here, times the volume gives me the rate at which they flow. So this, all four of these things, or really this times A times V, is the current I and then there's the L, d sine theta. If you're not convinced conceptually, you can always check the units. This was indeed a charge per volume. Area has length squared. That's a length per second. So the area is length squared and the velocity is length. Gives me a length cubed, which is cancelling the units of volume. The total charge is units of coulomb, and the per second left over from velocity gives me coulombs per second, which is consistent with I. So just another nice check that indeed that should be the current flowing through the wire, times the length of it that's actually in the magnetic field, times the magnitude of the magnetic field, times the sine of the angle between the current now and the magnetic field, because the current direction is the velocity direction. So instead of talking about the difference between V and B, we're now talking about the angle between the current and the magnetic field. Okay, so that is the force on a wire. And then again, that is a normal force, a usual, everyday Newtonian force. It's going to tell you what happens to this wire. Is it going to be pushed in which direction? We can use our right-hand rule and figure out the direction.